So please write these down. That'll help you start to learn it.
So we write this on our note side, right?
Yes, please. In the notes, just the next available page. And then we're going to talk about what it means. Okay. Okay, I'm there and I'm not frozen. And I'm assuming you're seeing this. I hope you are. Okay, a formal geometric proof, this is everything that needs to be in it. Okay, given in English is usually a verb. Terms in specified field, in specific fields will often have specific meanings. And here, the given, sometimes we use it as a noun. It's the given and it's the proof, even though both of those in general English uses are verbs. The given is what you're told to begin with, that you can assume. That's the given. Sometimes a diagram is part of the given. We'll talk about that. So most of the time, although not necessarily all the time, you'll need a diagram. And I'll show you how to do that. And then the proof, like I say, I'm using it as a noun. But you're given the answer. You're going to be told where to start and where to end. And your job is to get from the start to the finish, from the given to the proof. How you'll do that is with statements and reasons. You'll make a statement and then you'll say why you can make it. That's your reason. These are the items. The reason. You may use that it's given. You may use that it's a definition. You may say that it's a postulate or axiom, a property or a theorem. You can use those. For example, you can't say they look the same. That's not going to do it. Okay, you have to have a good justification for it. And I'll show you how we work all this out. Okay, here's a word you'll probably want to know. Well, 3 words you'll probably want to know. It's Latin. If you've watched Big Bang Theory, you've heard this a lot. QED, quod erat demonstrandum. It's Latin. Thus it is demonstrated, thus it is proven, something like that. QED. You've probably heard QED a number of times, not on Big Bang Theory, but if you've watched Big Bang Theory, you've heard it a lot of times because they say QED all the time. QED is the mathematical equivalent of, oh, I don't know, like if you're a sports fan, like football, like one of the players makes a touchdown and he runs across the line and then he does a little dance and throws the football up and all that kind of stuff. That's the football equivalent of QED, or taking a victory lap, or all that kind of stuff. QED says, I am done and I am good. Okay, QED. That's the phrase that my understanding is used worldwide. It's Latin, QED. So when you're done with the proof, if you want to take a victory lap, you just put QED. Say like, I am done and I am good. And I am frozen. It's just one of those days, folks. Let me see if I can get it unfrozen. Okay, can you see the diagram or does it say QED still?
I see the diagram.
Okay, good.
Yes.
So this is what it's to look like physically. Again, we're training your minds to be orderly and to think through every detail and justify every detail. This is the form we're going to use right now and for most of the year, although not exclusively, but for right now, we'll use this form exclusively. So it has to physically look like this when you've done a proof. You'll write the given. You are given the given, and you'll be told what it is. You'll write the proof, and you're told what you're supposed to prove, and you write it in there. So you know where you're to start, where you're to end, and your task is to get from the start to the end, from the given to the proof. You'll draw a diagram over here. Sometimes the diagram is part of the given. You're given the diagram, and sometimes you need to draw your own based on the facts that you're given. It's to physically look like this. You're to draw a big T. You're to actually write the word statement or statements. Actually write the word reason or reasons. Then we'll have a bunch of statements and a bunch of reasons why we're allowed to say it. We'll number them. For example, the first item here could be number 1. You'll put your first thing here. It'll often be what you're given. Some people just automatically put the given as the first statement, and that's fine. You'll get a sense as you do them how you like to do it. But the reason that's also numbered 1 has to be the reason why you're allowed to write the statement. So you write a statement, and why was it okay for me to do that? You put the reason here. Then you write your next statement, you put the reason why you're allowed to do statement number 2. And 3 and 4 and 5 and down to how many ever you get. And the last one will always be the proof. What you're supposed to prove. And you'll have to have a reason there too. And then you can do your dance in the end zone and put QED if you want to. If you don't put QED, it's still okay, but it's just kind of fun to know that. Quod erat demonstrantum. I am done and I am good, basically is what that says. Okay, I'm going to go through a couple of examples so that you can begin to see what this looks like. Okay. And a whole lot of what this unit is on learning to do this, learning to think logically. We'll use it all year long, but we're going to have a few examples of being able to do it properly. If this is in your textbook, you don't need to write it down. You can grab your textbook if you want. I don't even know what page it's on, but it's in lesson 2.6. 4 or 5 pages of lesson 2.6. It looks just like this. Okay, so it's called a 2-column proof by most folks, or a formal geometric proof, because it has 2 columns, and that's the form we're going to use. There are other forms that we'll use from time to time, but right now we're using a 2-column proof. Okay, I'll look at this one a little more closely. The given and the proof. Okay, so again, the statements are going to be working from the given to the proof using good logic and reasoning. And then the reasons will be why you're allowed to do that, why you're allowed to make the statement. I'll make it a little bit bigger so you can see this. Okay, so here we are given that angle 1 is congruent to angle 2. Okay, that's congruent. So we're talking about the shape of angle 1 and the shape of angle 2. So we draw 2 angles that appear the same, and we'll label them 1 and 2. Not much of a diagram for this one. Okay. So what we're given is that 1 equals 2, but we will need to prove that 2 equals 1. We need to use established reasons to do that. So we'll start here with the shape of angle 1 is congruent to the shape of angle 2, and that's given. It's given right there. Okay, you got to have your eye on the end. You got to know where you're going. Okay, I need to get it switched, but I know that the symmetric property is going to apply to numbers mainly, equality. And so I need to make this into a number instead of a shape. You say, well, how can I make an angle into a number instead of a shape and consider it as a number instead of considering it as a shape? And I say, oh, okay, I talk about the measure of it, that's a number. The measure of angle 1 is congruent, it equals to, because it's a number now, the measure of angle 2. So now I'm talking about when you measure angle 1 and angle 2, it's the same. Why am I allowed to say this? Because that is the definition of congruent angles. Congruent angles having the same measure. Congruent angles are angles with the same measure. You remember a definition is biconditional, which means we can say it frontwards and backwards. This one's probably actually a backwards one, but either way is the same because they're biconditional. So now I've converted it to a number and said that they're the same. Now I can flip-flop the equation because it's numbers using the symmetric property of equality. Officially, that's the whole thing, symmetric property of equality, but I'll never count it wrong if you don't put of equality. If you just put symmetric property, that'll be fine when you're doing your proofs. And you can abbreviate prop instead of property, that's fine. Okay, okay, so now I have, why did I do this? Why did I switch it? Because I'm looking where I'm going. I want the measure of angle 2 to be first. I want the shape of angle 2 to be first and 1 to be second. I've now switched the measure because it's a symmetric property of equality. And now I can go back to the shape with congruent, the definition of congruent angles. So now we've just used the definition of congruent angles both ways, coming and going. It's biconditional. You can do that because it's a definition. Okay, I could put a big QAD here and take a victory lap. So again, notice this is really picky-tacky, tacky-tacky, picky-tacky, right? Okay. So we started with shape 1 equals 2, and we want to prove shape 2 equals 1. We realized that we needed to go through numbers so that we could use the symmetric property of equality. You've got to be a real detective on doing this thing. Okay, you've got to be a real detective, and you have to be remembering where you're going. As you get into longer proofs, you'll start to realize that sometimes it's easier to start with the proof and go backwards to the given. Some people's logic just runs that way. You can work it either way you want. You can start in the middle, you can start at the beginning, you can start at the end. It doesn't matter as long as when you're done, you have a series of statements that follow one after the other and a reason why you can make each statement. Like I say, sometimes it's easier to start with the proof and work back up to the given. So I'll do another one here. This one is a word problem. Sometimes you won't be given it in math and you'll have to translate it into math. So I'll read this here for you. Walking down the hallway at the mall, you notice that the music store is halfway between the food court and the shoe store. The shoe store is halfway between the music store and the bookstore. Prove that the distance between the entrances of the food court and the music store is the same as the distance between the entrances of the shoe store and the bookstore. Okay, that's a lot of words. So you're going to need to draw a diagram. Here's one here that lines them up in order. So you read through it and you figure out it's as you're walking down the hall, it's food, then music, then shoe, then book. So you put them in here. Okay, now you'd like to mark that food and music is the same as music and shoe, and you'd also like to mark that music and shoe distance is the same as shoe and bookstore, because that's what the words of the problem told you. So you'd like to be able to mark that AB is equal to BC. You'd like to be able to mark that BC is equal to CD, but you can't do it on this one drawing, because once you start putting hash marks in, you're going to have 3 hash marks there. You'll have 1 here, 2 there, and 3 there. And you can't put more than one set of hash marks in one line segment. So you just can't do it that way. So what you have to do to be able to understand it is write two drawings that both do the same thing, that say both of the two circumstances. So here's one of the circumstances that was described in the words. AB is the same as BC. So the same between the food and the music and the shoe. And then I've done it again to say BC is the same as CD. Between music and shoe is the same as between shoe and book. You can't put them on the same diagram because BC has two different hash marks in it, and we're not allowed to put two different hash marks in one segment. So that's the reason why you have to split it up. Okay, so let's look at how this would be proven. Again, this one is in your textbook in 2.6, and you're welcome to look back at it. I don't recommend that you try to write it down right now. I'd rather you just look and watch. Here's how you'd set that word. Ollie. Here's how you'd set up that word problem as a formal geometric proof. Okay, we'd have two diagrams that show it, which we just talked about. Then given, notice I've written it out in geometry language. B is the midpoint of AC. You might also say B is halfway between, but it's okay to say that once we've done this, because this is actually a little bit of a reason. And then C is the midpoint of BD. And we want to prove that AB is the same as CD. AB is the same as CD. And so here are statements that go through it to do it. Okay. We've written what we're given. We translated the English into sort of math and wrote it down here for us. A lot of the things that we'll deal with in geometry will actually be numbers. And this is not uncommon to write things like this. And a reason is that we're given that. So what do we go through? That B, you could have set this up differently and these steps would be different, but let's just go through this one because this one works. That's the thing about proofs. Most of the time, there's more than one way to do it. And as long as each statement follows from the previous statement and each reason justifies writing that statement, then you're fine. So like when I grade a test on this, it's a lot of trouble to grade it. It takes a long time to look at what each individual student did in their logic. I'm glad to do it if you'll learn to think right. I'm not sure how I'm going to do it virtually, but I'm going to have to figure out something. Okay. Because I want you to know this. It's important that you order your thinking. All right. AB is the same as BC. That's the definition of midpoint. Midpoint divides a segment into two equal segments. Same deal here. BC is the same as CD, definition of midpoint. Notice that since those both have the same reason, I could have written them both as 2 and then just wrote 2 as definition of midpoint. You're going to get a style. You're going to get into a style. You're going to get into your groove about how to write proofs. I personally prefer doing it this way, which is the way the book did it on this one, writing out every one with its own little number and its own little number here. But you may like it the other way, and as long as it's justified and it works, then it's fine. All right, so now then we have that AB, okay, this is shape because it's congruent, right? AB, definition of midpoint is it divides into two congruent segments. Here's the two congruent segments. So transitive property of congruence. Two things that are congruent to the same third thing are congruent to each other. Does everybody see that? They're both congruent to BC, so AB and CD are congruent to each other. Transitive. You don't have to write of congruence unless you just want to. Transitive property is good enough, and you can abbreviate property as prop if you want to. So then going from the shape is the same as the shape, the measure is the same as the measure. That's the definition of congruent segments. They have a measure. Okay. So again, you don't need to write this down. It's right there in your textbook. This is taken straight from the textbook. I just wanted to walk through one of them with you. Okay. Now I'd like to talk through a few theorems. These are things that we've talked about and we're now formally stating them as theorems. And I froze. It really is one of those non-tech days. I apologize. So I need to get that off and make this go away and redo it. And that should work. Let's see. There we go. You should be able to see it now. Okay. If you would write this down. Some of these are like no duh. Like really, you're actually writing that down, but you do need to have this formal training. Thinking through every itsy bitsy teeny tiny step. I guarantee you it will benefit you. Okay, right angle congruence. All right angles are the same. A reminder, a postulate or axiom is something that we accept without proving, not that it can't be proven, but that we're not going to prove it. A theorem is something that we do prove. I'm not going to write down the proof, but as you're looking at it, I'll just talk you through it. So if we're given that this is a green right angle and a red right angle, we can say this right angle is equal to 90 degrees because that's the definition of a right angle. And the same deal here, the red one is also equal to 90 degrees. So the measure of this angle is 90, the measure of this angle is 90. The transitive property says that the measure of the two angles are the same. So we'd have measure of green is equal to measure of red, and that would be by the transitive property. And then we'd say that green is congruent to red because of the definition of congruent angles. Because it's the definition of congruent angles is that they have the same measure. Okay, so I just kind of spoke through a proof that we could do of this theorem. Then the next one here, a linear pair. We've already talked about this one. I'm not sure whether we called it a postulate, but we'll call it a postulate now if we haven't. If two angles form a linear pair, then they're supplementary. You'll recall that a linear pair means that when they share a common side, that the outside of both of them is a line. A line is 180 degrees. So that's how we could prove this one. I was going to walk through a proof, but I'm seeing it's a postulate, so we're going to accept it without proving it. Many postulates can be proven, we just don't do it. So I think you already knew this. Now, when you want to use it, you can call it the linear pair postulate. Congruent supplements. Again, this one's pretty obvious. Okay, congruent supplements. If two angles are supplementary to the same angle or to a third one. If two angles are supplementary to the same third angle or congruent angles, then the two angles are congruent. Okay, so what do we have here? We're given if they're supplementary to the same angle. So 1 plus 3, angle 1 plus angle 3 is 180 degrees. That's what we're given, and that's the definition of supplementary, is that the measure adds to 180. Angle 2 plus angle 3 add to 180 because that's the definition of what it means to be supplementary. It's to add to 180. By the transitive property, this is equal to 180. The second statement is equal to 180. Therefore, the first one is equal to the second one. Subtract angle 3's measure from both sides, and you're left with angle 1 is equal to angle 2's measure, and that therefore they're congruent because of the definition of congruent angles. Okay. So again, these are not difficult. Why are we doing it? We're doing it because we're learning to go delicately and precisely from one step to the next. congruent complements is the same, and it would, if I talked you through it, it would be the same. So we also have, if two angles are complementary to the same angle or to congruent angles, then the two angles are congruent. This one we haven't formally stated, but this is one of those gut things that it's just got to be that way. A theorem, so we can prove it.
Dr. Hamilton,
Sir?
could you go back to the congruent complements?
Here you go. We got plenty of time. Take a little while longer.
You can move on now.
Okay, and just to show you on the supplements, there's a proof in your textbook of what I just said. If you didn't catch to what I was saying and seeing, it's better for you. So this is also in the textbook. It's the proof of congruent supplements, and the congruent complements is the same. This is what the steps I just talked you through. So that's there if you want to look at it. Okay. Then vertical angles. Now this is one of those, it has to be that way. It can't be anything else. Yeah, we can prove it, and I have a proof here of it. But let's look at just instinctively why this has to be true. Again, theorems are things that we need to prove. Postulates are things that we take as without proof. Let's just look at what happens. Recall that vertical angles are always going to be staring each other down across the vertex corral, show down at the vertex corral, right? So it's the angles that are across the vertex. Doggy and froggy, right? Okay. So, say for example, this one upper left and lower right. Watch what happens as I move the red line. The one on the left is getting smaller. Oh my goodness, the one on the right is getting smaller. That's magic. No, it's not. Okay, what if I go, what about getting bigger? It worked for getting smaller. Will it work for getting bigger? Let's see. Okay, the one on the left is getting bigger. The one on the right is getting bigger. And notice that they're getting bigger by the same amount and at the same rate. Why? Well, part of it is because the lines are straight. We can work through it with a whole bunch of proofs on different ways. We can talk about congruent. We can talk about congruent supplements. We can do it, prove it a whole bunch of different ways. But for our purposes for today, it's fine just to recognize why it works. It's good for you to notice why. The operation of what happens when one of the angles change. So in an intersection here like this, the two vertical angles in the top and the bottom will always remain congruent. So if I'm looking at the upper right and the lower left, they get smaller at the same time at the same rate. They get larger at the same time at the same rate. So there's a proof of that with congruent supplements that I'm not looking at right now. Okay. So that's vertical angles congruent. Vertical angles are congruent. It's just as easy to write out the whole thing. If you would, please find this. I mentioned it, I had it out at the beginning. It's a paste in for your cipher. It's the ones that we just did. They're written out. The diagrams are here. All of the things I just asked you to write are here. Again, the reason why I ask you to write it is to help you to learn it. Now we're going to paste it into your glossary. And so you'll have it in two different places. So go to your cipher, to the glossary, and find the next available page, whatever that is. The last thing I did was his properties. So mine will just go right here. Okay. And remember, what you're to do now is to put in your page number. So get your glue stick, glue it down really good, paste it in, and find where you were just writing and see what your page number was on that page. So this might be on page 27 and this one here on page 28 or something like that. Depends on how big you write. So go ahead and paste it in and put in your page number.